Welcome! In this video, we're going to introduce a series of equations that we're going to use throughout this course to solve or look at kinematic problems. So in a previous video, we looked at the definition or the formula for acceleration, and acceleration is just the rate of change of velocity with respect to time. And we looked at this formula where we saw the change in velocity over the change in time is equal to the acceleration, or v final minus v initial divided by the change in time is equal to the acceleration. Now, in this course, we're not going to really look at too many problems where acceleration is changing. So most of the kinematic problems that we're going to look at will assume either an average or a constant acceleration. And all of these formulas that we're going to look at in this video are based on that assumption, that there is an average or a constant acceleration. The other thing with these formulas is that in previous formulas we've seen the change in time expressed as the final time minus the initial time, or delta t, but the time in all of these equations is always delta t, always the change in time, and it's always a positive value. So most of the time we just use the shorthand of t, and t just if you see t in the formula, that means the change in time, or the delta t. So if we take this acceleration formula that we have here and we rearrange it by multiplying both sides by delta t, or by t, we can rearrange that formula to look like this. So we can say that the final velocity is equal to the initial velocity plus the acceleration times time. And this forms the basis of our first formula. But we can look at that formula and say, okay, if there wasn't any acceleration, so if acceleration didn't exist, all that formula tells us is that the final velocity is equal to the initial velocity. In other words, there's constant velocity if there's no acceleration. But if we do have acceleration, then the final velocity is not going to be the same as the initial velocity. It'll be the initial velocity plus some component due to the fact that there's acceleration. So this formula is the first of these four kinematic formulas that we're going to look at. For the second formula, we're going to go back a bit and look at our formula for displacement if we know velocity. And so if you recall from a previous video, we said that the change in displacement, if there's velocity, is equal to the velocity, or the average velocity, times the change in time. And this formula works fine as long as you've got an average or a constant velocity, but it doesn't take into account a situation where the velocity is changing. In other words, where there's acceleration. So we have to modify this formula if we've got any acceleration. This is the modified version of that formula. Now, the derivation of this formula is beyond the scope of what we want to do in this course. But if you take a look at this formula, it's very similar to the previous one, and you can see that the final displacement is actually made up of three components. It's made up of the initial displacement plus a displacement due to any initial velocity times the amount of time that the event took place, or the delta t, plus a component that takes into account the fact that we have acceleration, or we have a changing velocity. So we can see in this formula that if we, again like the previous formula, if we don't have any acceleration, then this formula reduces back to what we had before. So we have the change in displacement is equal to the v initial, which would be the same as the v final if there's no acceleration, times time. But when we have acceleration, we have to add this other component in here. So this formula becomes our second in our series of four kinematic formulas. So let's take a look at a relatively straightforward example looking at that second formula. So this example is set up to use that second formula. So in this example, we're going to talk about curling, and we have a curler that lets go of a rock, and when he lets go of the rock's going at 4 meters per second. And the rock slows down at a rate of 0.5 meters per second squared. And so the question asks, if the rock travels for 8 seconds and then stops, how far will it go after it was released? And we're going to assume in this question that the rock travels without any curl. So it's a straight handle. It goes straight down the ice. There's nobody sweeping it or anything. So it just goes straight down the ice. And so when we're solving a problem like this, it's always good to start with a diagram and a coordinate system. So here's our rock, and we have to, in this case, we're only talking about one axis down the sheet of ice, but we do need to set up a coordinate system. So we do need to say what's positive and negative. And so for this problem, I'm going to say that positive is down the sheet of ice. So in the direction that the rock was released, we're going to say that's positive. So the next step when you have a problem like this is to decide what is your initial and final condition. What time points is the start of the problem and the end of the problem? This one's pretty straightforward. We can say that the initial time is the instant that the rock was released. That's the start of the problem. That's the initial condition. And the final condition, or the end of the problem, is when the rock stops. So because the question's asking how far is the rock going to go after it's released. So from when it's released to when it stops. So that's our initial and final condition. And then the next thing we should do is figure out what do we know in terms of the kinematics about those initial and final conditions. So under the initial condition, since we're only interested in how far it's going after it's released, we can say that our initial displacement is 0 when it's released. And we also know what the initial velocity is. It's 4 meters per second. And since we've already decided that the coordinate system is going down the direction of the way the rock was released, our initial velocity is a positive 4 meters per second. In the final condition, we're looking at the final displacement. We actually don't know what the final displacement is because that's what the question's asking. It's asking how far will it go after it's released. In terms of a final velocity, well, based on the question, we know that the rock has come to a stop, so the final velocity is 0 meters per second. So that gets us our initial and final conditions. And there's two more kinematic quantities that we need to see if we know. One of them is the delta t, or the amount of time that it took. And so from the question, we know that it took 8 seconds to go from initial to final. The last kinematic quantity that we want to see if we know is acceleration. So in this case, we know the acceleration from the statement in the question that said the rock slows down at a rate of 0.5 meters per second squared. So that tells us that the velocity is changing at a rate of 0.5 meters per second squared. And the fact that it says the rock slows down allows us to assume that the acceleration is going the opposite direction of the way the rock was released. So the acceleration is going in that direction of that red arrow, and so we know that that's the negative direction according to our coordinate system. So in this case, our acceleration would be a minus 0.5 meters per second squared. So now we have all of the kinematic quantities that we need to solve the problem. So we can look at the formula and just put in the values and see what we get. So for this formula, we have d final is equal to our d initial, or our initial displacement, which is 0 meters, and plus our initial velocity, which is 4 meters per second, times our time, which is 8 seconds, plus 1/2 times our acceleration, which is minus 0.5 meters per second squared, times our time, which is 8 seconds squared. So our d final then is 0 meters plus 32 meters. If you do the math, 4 times 8 is 32, minus 16 meters. So the 1/2 times 0.5 meters per second squared times 8 seconds squared will get you your minus 16 meters, which means our final displacement is 16 meters. So you can see from this that if there was no acceleration in the negative direction, the curling stone would have traveled 32 meters in 8 seconds. But because of the acceleration in the opposite direction, it actually only travels 16 meters. So we've introduced two kinematic equations, and we can actually take those two kinematic equations and substitute them back and forth into each other and come up with an additional two kinematic equations. And these are simply based on those first two. And again, we're not going to go into the derivation of these equations. The third and fourth equations are useful in a couple of different situations. So the third equation, if you notice, it doesn't have time explicitly in the equation. So that equation is sometimes useful when you don't know time explicitly. You know other variables, but you don't know time. And the fourth equation, if you notice, it doesn't have acceleration explicitly. It still takes into account acceleration, but acceleration is not a variable in the formula. So if you have a situation where you don't have acceleration explicitly, but you have some other variables, this fourth formula can be useful. So these four formulas are used for the majority of the kinematic problems that we're going to take a look at in this course. And I would encourage you to look at the linear kinematic problem sets as a lot of those questions are applications of these four equations.